Hello everyone, today we will continue learning about the derivatives of functions. In the previous class, based on the definition of the derivative of a function, we calculated the derivatives of the following 6 commonly used functions. Do you remember what their derivatives are? Let's reminisce together. The derivative of function fx with constant c is equal to 0. The derivative of function fx equal to x is equal to 1. The derivative of the function fx equal to the square of x is 2x. The derivative of the function x cubed is equal to 3 times x squared. The derivative of function fx equal to 1 of x is equal to negative 1 of x squared. The derivative of the function fx equal to the root of x is equal to 1 of 2 times the root of x. So let's observe which category of basic elementary functions the other 5, except for the first one, belong to among these 6 functions. By observation, we can see that these functions all follow the form that fx is equal to x alpha power, so they are all power functions. And the power exponent alpha is equal to 1, 2, 3, negative 1, and 1/2, respectively. Now let's observe, can you find any relationship between their derivatives and functions? So if we write the derivative of fx equal to 1 of x as the negative second power of x, and then write the derivative of fx equal to the root x as the negative 1/2 power of x multiplied by 1/2. Let's take a closer look at the relationship between the fx function and its derivatives. Through observation, we can see that we have mentioned the power exponent alpha of function fx as the coefficient of the derivative. Subtracting the power exponent by 1 as the new power exponent yields the derivatives of these power functions. So this rule also holds for general power functions. That is to say, for the power function fx, it is equal to the alpha power of x, and its derivative is the alpha of x multiplied by alpha minus 1 power. Alpha belongs to q, and alpha is not equal to 0. Therefore, we obtain the derivative formula of the power function. So, besides power functions, what other basic elementary functions are there? What are their derivatives? We have studied exponential functions, logarithmic functions, and trigonometric functions in addition to power functions. You may say their derivatives, but we can also calculate them based on the definition of derivatives. In fact, for other basic elementary functions, we can indeed calculate their derivatives one by one according to the definition of derivatives. However, due to our current incomplete knowledge structure, the calculation process of derivatives is still somewhat difficult. Therefore, we need to provide the derivative formulas for these basic elementary functions without the need for proof. In the future, we can use it directly. So the derivative formula for these basic functions is, firstly, fx equals the derivative of constant c, which is equal to 0. The second one is that fx is equal to the power of x alpha, and when alpha belongs to q and is not equal to 0, its derivative is the alpha of x multiplied by alpha minus 1 power. We have obtained the derivative formula of the power function. The third one is that fx is equal to sine x, and its derivative is cosine x. The fourth one is that fx is equal to cosine x, and its derivative is negative sine x. So we have derivative formulas for sine and cosine functions. Fifth, when fx is an exponential function, we obtain that fx is equal to the derivative of his power x multiplied by ln a. So we can find that when a equals e, ln a is equal to 1. Therefore, specifically for exponential functions with e as the base, their derivative is itself. The sixth is that for the logarithmic function fx, the base is a, and the logarithm of x, a, is greater than 0 but not equal to 1. So its derivative is equal to x multiplied by 1 of ln a. Similarly, when a equals e, ln a equals 1. So specifically, if fx is equal to ln x, then the derivative of fx is equal to 1 of x. So what are the structural characteristics of these derivative formulas, and how do we remember them? First, the derivative of a constant function is equal to 0. The second one, the derivative of a power function, is obtained by taking the original power exponent as a coefficient and subtracting it by 1 to obtain the new power exponent. Third, the derivative of a sine function is a cosine function. The fourth one, the derivative of the cosine function is equal to the negative sine function. For an exponential function with e as its base, its derivative is equal to itself. So, taking any constant a that is greater than 0 and not equal to 1 as the base of an exponential function, its derivative is equal to itself multiplied by ln a. When the logarithmic function f(x) with e as the base is equal to ln x, its derivative is equal to 1 of x. So for any logarithmic function with a constant a as its base that is greater than 0 but not equal to 1, its derivative is equal to x multiplied by 1 of ln a. Next we will solve some problems based on the formulas of these derivatives. Let's first look at finding the derivative of the following function. Let's first analyze such a problem. I want to request the derivative of a function. First, we need to determine the type of function, and then find the corresponding derivative formula based on the derivative formula table of basic elementary functions. Then, we can calculate their derivatives. The first function y is equal to the 2/3 power of x, which should obviously be a power function. So the derivative of a power function is equal to the alpha of x multiplied by alpha minus 1 power. In this problem, alpha should be equal to 2/3. The second one, this should be a logarithmic function with a base equal to 2. So the derivative of a logarithmic function is x multiplied by 1 of ln a. Here, a should be equal to 2. Let's explain it specifically. The derivative of function y is equal to the 2/3 power of x. According to the derivative formula of basic elementary functions, it should be equal to the 2/3 times x to the negative 1/3 power of x, simplified as 2/3 times x to the negative 1/3 power. The second derivative, which is the logarithm of the base x, should be equal to x multiplied by ln 1/2, according to the derivative formula of basic elementary functions. So we have obtained the derivatives of these two functions. Now let's take a look at how to find the tangent equation of sine function y equal to sine x at point 0. Let's first analyze this issue. We already know that point 0 is a point on the tangent line, which is a point on the straight line. So we only need to calculate the slope of the line again to write the equation for this tangent. And through the geometric meaning of the derivative, we know that the slope of the tangent is equal to the derivative of this function at x equals to 0. According to the derivative formula table of basic elementary functions, we already have the derivative of sine numbers as cosine functions. Therefore, with the derivative of sine functions, we can correspondingly calculate the derivative value at x equals to 0, that is, the slope of the tangent line. Combined with the slope of the point, the equation of the tangent can be written from the oblique line equation of the point. Let's explain it specifically. Because the function y is equal to sine x, the derivative of y is equal to cosine x. Therefore, the derivative of the function y is equal to 3x at x equals to 0, which is equal to 1. The slope of the tangent is equal to 1. So we can write the equation for this tangent line as y minus 0 equals 1 times x minus 0. Further simplifying and organizing it as y equals x is the tangent equation we require. Now let's take a look at a practical problem. Assuming an annual inflation rate of 5% in a certain area over a period of 20 years, the relationship between price P and time is expressed as PD being equal to the T power of 1 plus 5% of P0 times, where P0 is the price at which T equals 0. If we assume that the P0 of a certain commodity is equal to 1, what is the approximate rate of price increase for this commodity in the 10th year? We need to be precise to 0.01 yuan per year. Let's first analyze what mathematical knowledge is involved in such a practical problem. According to the conditions of the question, we have a formula for the relationship between prices and time, where Pt is equal to the T power of 1 plus 5% of P0 times. From this relationship, we can find the type of the function. When P0 is equal to 1, this function should be an exponential function, and the base should be 1.05, so this is an exponential function with a base greater than 1. So this function is an increasing function, so the price rises over time. So the speed of price increase should correspond to the derivative of this function. So from the derivative formula of basic elementary functions, we have obtained the derivative formula of exponential functions. We only need to substitute t equal to 10 to obtain the derivative value, which is the rate of price increase. Specifically, according to the derivative formula table of basic elementary functions, we can obtain that the derivative of function pt is equal to the t power of 1.05 multiplied by ln 1.05. Substituting t equal to 10 again, we can obtain that the derivative of t equal to 10 is equal to the 10th power of 1.05 multiplied by ln 1.05, which is approximately 0.08. So, in the 10th year, the price of this product increased at a rate of about 0.08 yuan per year. So, if the P0 of a certain product is equal to 5, what is the approximate rate of price increase for that product in the 10th year? According to our recent analysis, to determine the rate of price increase, we need to find the derivative of this function when t equals 10. So we can calculate the derivative of the function PD equal to 5 times 1.05 to the power of t, and then use t equal to 10 to find the corresponding derivative value. So the next question is, how to find the derivative of the function PD equal to 5 times 1.05 to the power of t? We know that according to the derivative formula table of basic elementary functions, we can calculate the derivative of the function ft equal to 5 and gt equal to 1.05 to the power of t. But we cannot find the derivative of PD equal to 5 times 1.05 to the power of t. How should the derivative of function PD be calculated? What is the relationship between its derivative and fg's derivative? This will be the main content we will study in our next class. Let's summarize these 3 examples below. Through these 3 examples, we have further familiarized ourselves with the derivative formula of basic elementary functions, the process of finding derivatives, and the method of finding tangent equations of curves. We have also experienced the practical application of derivatives through practical problems related to the differentiation of exponential functions. Through example 2 and example 3, we found that we can use the derivative formula of basic elementary functions to first calculate the derivative, and then substitute the specific value to obtain the derivative value at a certain point. And there is no longer a need to use the definition of derivatives to find the derivative value at a certain point. This can greatly simplify the calculation process. In the follow-up of example 3, we found that the derivative of the function PD, which is equal to 5 times 1.05 to the power of t, cannot be directly calculated based on the derivative formula of basic elementary functions. Therefore, we propose a new question, which is what is the relationship between the derivative of the function PD and the derivative of the function ft equal to 5 and gt equal to 1.05 to the power of t. Below, we will summarize the knowledge content learned in this lesson. In this lesson, we mainly studied the derivative formulas of basic elementary functions, including exponential functions, logarithmic functions, power functions, as well as the derivative formulas of sine and cosine functions, and special derivative formulas for exponential functions with e as the base and logarithmic functions with e as the base were provided. With these derivative formulas, we can directly calculate the derivatives of these functions in future calculations without the need to use derivative definitions for calculations. This can greatly simplify our computational workload. Therefore, these derivative formulas need to be memorized and mastered by everyone. That's all for this lesson. Goodbye, everyone.